Good day everyone. This is going to be a short video on how to use Excel to plot a non-linear curve. And we are going to be using the Van Genich 1980 equation that is being used to plot suction versus volumetric water content. So the first thing to do in this case is if you have some feed or laboratory data that you have measured in PSI, in this case, I would like to plot my suction in centimeter. So I try to convert it first to kPa using Excel, then I converted it to meter, then I converted it to centimeter. So I'm interested in plotting my suction in centimeter against my volumetric water content. So the first thing to do is we need to plot the volumetric water content and the suction as the result is being taken from the lab. So you go to insert, scattered plot, and I'm going to select my data here, add series. I'm going to name this feed or lab data. And my x. So I'm going to be plotting my suction on the x-axis, and I'll be plotting the volumetric water content on the y-axis. Okay. So this is my plot. I need to change the suction to a logarithm scale. But first, I don't need the decimal places, so I can change this to logarithm scale. And checking this, I don't really have any data that is going beyond 10, so I can make my minimum 10. Good. The next thing, so we can clarify our axis, we can just add the axis title and make this suction and this in centimeter, and we also make this volumetric water content. I can add theta as the symbol for that. There I have my theta. So the next thing is now fitting a line for this. How am I going to do this? There's an equation that you can use to do that, and that's what we have here. So for the equation, you need to understand the parameters. We have some constants in the parameters. So the first parameter is this alpha, and you can see from the formula, it's like probably averagely 1 over the bubbling pressure. Let's say around this area we're having the bubbling pressure in this area because this is the saturation. From the point the saturation starts dropping water, that's where we have the bubbling pressure. And the bubbling pressure, we can say it's about 509. So we can just say this is equals to 1 over 500. That's just the parameter we are starting with. And the reason this is important is sometimes it is better to start your fitting parameters with numbers that are close that to the real numbers because it's going to help you to get to convergence as fast as possible. So the theta S is talking about the volumetric water content at saturation, and from here you can see it's 0.463, and the theta R is the residual water content. From here it's about 0.139, so you can say 1.139. So in this case, I know from the textbook I snipped this, they are using their n to be equals to 1 over 1 minus m. In my case, I will be reversing it. I'm going to make my m the subject of the formula. So my m equals to 1 minus 1 divided by n. And for my n, I can just write 2 as a starting point. So the next thing is, what do I want to solve for? I want to solve for the volumetric water content now. I need to input this equation in what I want to fit. That's why I named this volumetric water content fitted. So it's going to be equals to, first we have the residual water content. I'm going to fix this. Then we have plus the saturated water content minus the residual divided by, we have 1 plus, we have alpha. I'm going to fix it to alpha multiplied by our suction. So my suction is F. So for me to be able to do that, yeah, F. Then raised to power my N. I'm going to fix it. Then all together raised to power M. And I'm going to fix that too. So I have my equation written. I'm going to press enter. Then I can drag this across. Then I can go back to my table, chart design, select data. I can now add the fitted plot now. So let me call this fitted data. and my x is going to be the matric suction in centimeter, and my y is going to be this fitted volumetric water content. Okay. Okay, so this is the fitted line now, but what we are interested in is making this line to give us the best fit across these data points. And to do that, next thing we need to do is we need to first calculate the error between the actual and the predicted. Actually, the square of the error, because that's what we are going to try to minimize as we are solving for the equation. So that's the square of the error. I'm going to draw it across this line. So now we can go ahead to fit our line. So to fit this line, we are going to use what we call solver in Excel. If you don't have it in your Excel, you might just need to go to your file, then you go to, you just need to go to file, then you go to options. So during your option, you're going to see adds in, then under the adds in, you can click solver and add it. I already have it in my Excel, so I don't need to do that. Cancel. So going back to solver now. So what am I trying to do? I want to try to minimize this point. So I have it. So this is what I'm minimizing, and I'm trying to change these four parameters. In this case, you can have different options. In my case, since I have my theta saturated to be 0.403, I can make it a constraint that I want that particular parameter to be equals to a certain value, and I want my residual to be equals to this. If you want to change anything, you can just click this. You can change, or if you want to add new constraint, you can add new constraint. In this case, it's possible you can make your theta saturated to be greater than or equals to, because it could be greater than the value you have there, and you can also make your residual, you can give it new relationship constraint. But in this case, I'm going to leave it this way. So I'm just going to press solve. There we go. So you can see that this has changed. But for me to really understand or differentiate between the 2 points, I can come and click on this. Actually, I need to double click. So I can come to this version. I can make the solid line. I can remove the marker option. Or better still, I can just make it a broken line. Broken line. So from there, this is the fitted data point, and these are my parameters. So my alpha is actually 0.001, my theta saturated, this is my theta residual, this n and this is m for this parameter. Thank you for watching. Goodbye.